Okay, this video is going to be about estimating population mean. Large samples and standard deviation is going to be known. In the previous section, we focused on the population proportion parameter. What proportion of the population has this or that trait? And we created confidence intervals for that. Now we're asking, well, what is the average of the population? What is the average height, whatever the average is that we're interested in? And we're going to create a confidence interval for a specific type of case when we have large samples that are going to be greater than 30 and population standard deviation is known. Now, here's kind of a problem with this. This is really hypothetical because usually if you know the standard deviation, then in calculating the standard deviation, at some point you know what the population mean is. So this is a really unrealistic situation. We'll go through it, but it's really unrealistic to have sigma known, but you're creating a confidence interval for the mean. Okay? So as usual, as the previous section, we're going to go through those same exact definitions, but everything is going to be pertaining to the mean. Okay? Assumptions for confidence intervals for the population mean. Large samples is defined as samples that are greater than 30 and sigma is known. And just remember that data collected carelessly can be absolutely worthless, even if the sample is quite large. So it has to be a random sample, right? You have to account for all of the different things, or as many as possible, to make sure that you have a good, carefully selected sample. Here's some definitions that you might have seen already from the previous section. Estimator, a formula or process for which using sample data to estimate a population parameter. An estimate is a specific value or range of values used to approximate the some population parameter. And then the point estimate, which we did in previous sections, is a single value or point used to approximate a population parameter. So the sample mean, x bar, is the best point estimate of the population mean, right? That's a point estimate. Here's another definition for a confidence interval, a range or an interval of values used to estimate the true value of the population parameter. So we're going to get a lower bound and we're going to get an upper bound for our population mean. We might never know what the population mean is, but we can have a certain level of confidence that we have found an upper bound and found a lower bound for the population mean. Okay? As a reminder, remember that confidence intervals are used because they make more sense. It makes sense to have a range of values rather than just one point estimate. You don't know how far away you are from the actual population mean with a point estimate, with a point estimate, but with a interval of values, you do have a confidence level. So even though x bar is the best point estimate for the population mean, and S is the best population estimate for the population standard deviation, they do not give us an indication of how good they are. On the other hand, number 2 here says, a confidence interval gives us a range of values based on variation of the sample data, and also how accurate we want to be, the confidence level, right? So the width of the interval gives us an indication of how good the estimate is. The narrower the confidence interval, that means we're pretty sure. The width is called the margin of error, and we have separate formulas for the proportion and for the mean. So there's a degree of confidence that we have, proportion of times that the confidence interval actually contains the population parameter, right? How many times do I expect the population parameter will actually be in the confidence interval? So the degree of the confidence would be 1 minus alpha, often expressed as a percentage of value, usually 90, 95, 99% confidence level. So in those respective cases, alpha would be 10%, 5%, and 1%. And again, this goes exactly the same as with the population proportion that we were finding confidence intervals for, but now it's for the mean, the average. So here's interpreting confidence interval. So if we say the population mean is between 98.08 degrees and 98.32 degrees, what does this mean? This means that if we were to select many different samples of sufficient size and construct the confidence intervals, 95% of them, 95% of the confidence intervals would actually contain the value of the population mean. And then the above interval is one such interval given a sample. So take a sample, and at the 95% confidence level, you create this interval, and that means among the process of creating all of these intervals, we are sure that 95% of them will actually contain the population parameter. This is just one such example of the interval, right? We're not sure if this interval does actually contain the population mean, but because of our confidence level, 95, we're pretty sure that it does contain the population mean. It says here, we are very confident that this interval contains the population mean because it was constructed at the 95% confidence level. Now let me show you guys again the picture. The idea is we would be creating a whole bunch of these confidence intervals, and not all of them would necessarily contain the population mean, right? 95% of them would, like this one over here does not contain. And some of them would be wider, and some of them would be narrower, but 95% of them would contain the population mean. That's the idea of the confidence level. So the critical value that we would have to find is the number that on the borderline that separates the sample statistics that are likely to occur from those that are unlikely to occur. The number z sub alpha over 2 is a critical value that is a z-score with the property that it separates an area of alpha over 2 in the right tail of the standard normal distribution. So z sub alpha over 2 is going to be a positive critical value, a positive z-score. Here's a little picture of that. We can find this on our calculator by using inverse norm, right? Whatever our confidence interval is, we would have that be the middle portion, and then those alpha over 2, those portions you would use to figure out what the critical value is, right? What's that z-score that separates likely from unlikely values? And here's an example. Finding z sub alpha over 2 for 95% degree of confidence means that 95% chance that the values are between these two, negative z sub alpha over 2 and positive z sub alpha over 2, which means there's only 0.025 in the tails. To figure out what the critical value is, z sub alpha over 2, I would do inverse norm of 0.95 and 0.025, because that is the total area to the left of this z sub alpha over 2. So I would do inverse norm of 0.975. And when we do that, we would get the critical value, which is 1.96, right? 1.96, or the negative version would be negative 1.96. And that's how we would find the critical value, using inverse norm of the area to the left of the positive version of the critical value. And here's some common confidence levels and their corresponding z-value. So if we have a 90% confidence level, that means our z-score, the critical value, is going to be 1.965. If it's 95%, 1.96. We just found that one in the previous exercise. And then it keeps going with common confidence levels and their corresponding z-scores. Okay, you'll be getting used to those values showing up pretty often. Now, to complete our confidence interval, we need a margin of error that we're going to add and subtract from the point estimate, from the sample mean. So the margin of error, denoted by E, in the context here, this is margin of error, not expected value. This is the maximum likely difference observed between sample mean and the true population mean, right? What's the maximum likely difference between the population mean and the sample mean? And then we're going to add and subtract that amount, and we would get the confidence interval. The formula for the margin of error is different from that, from the proportion, because we have the mean here, and that is your z-score, z sub alpha over 2. And again, remember, this is really unlikely to have the population standard deviation, but that's what we get here. Population standard deviation divided by the square root of n, because we're taking a group, right? This comes from the central limit theorem, sigma divided by square root of n. Okay, and remember, we're basing this off of large samples, n is greater than 30. And then we would be able to use this formula. Margin of error is equal to the critical score times sigma over square root of n. So when can we use this critical value? We can use it when we have a sample that's greater than 30, or if it's less than or equal to 30, we have to be confident that the population must have a normal distribution. And sigma must be known, the population standard deviation. Now, as I've mentioned before, knowing sigma is largely unrealistic, right? It's unrealistic. If you know sigma, then you probably know your population mean as well, because you need your population mean to be able to find the population standard deviation anyway, per the formula. So those are the criteria for using critical values, z values. A quick note here on rounding. When using the original set of data, round confidence interval limits to one more decimal place than is used in the original set of data, one more decimal place. And then when you have the original data is unknown, but you're given summary statistics, right? The sample size, the mean, sample mean, and sample standard deviation, then use the interval limits to be the same number of decimal places as used for the sample mean, right? So whatever the sample mean has, use that same amount of decimal values. So let's do an example. Here's a study found the starting salaries of 100 college graduates who have taken a statistics course. So we know what n is. The sample mean was $43,704, and the population standard deviation, again, usually that's not known, is 9,879. Find the margin of error and the 95% confidence interval. So we need to find E using the formula z times sigma over square root of n, and then we need to subtract from the mean and add to the mean to get this confidence interval. And so when we go through that process, the margin of error here is z sub alpha over 2. We have a 95% confidence level interval, so we're going to have 1.96. We have previously found that one. Standard deviation is 9,879 divided by the square root of n, which is 100 graduates. And this is what we get. This is the margin of error, 1936.3. And that's what we would add and subtract from the sample mean. 43,704 minus 1,836, that's 41,768. And the same idea goes for 43,704, adding 1936.3 to that to get the upper bound for my confidence interval. Again, this is one example of a confidence interval that is created at the 95% confidence level. So based on the sample provided, we are 95% confident the population mean, the true mean of starting salaries, is between 41,768 and 45,640. Okay, now we just did that by hand. Let me go back to that. We did that by hand and found the confidence interval. Remember that there's a calculator function for this, and the calculator function is called z-interval. I'll post me doing exactly the same example using that calculator function after this video. Okay, so you go to stats, tests, z-interval, enter in the statistics, and you get your confidence interval. Here's a conceptual question to think about. Pause the video and think about how to answer this question for yourself. What happens to the width of confidence intervals with changing confidence levels? What happens to the width of confidence intervals with changing confidence levels? And one answer to that is the width of confidence intervals decreases as the sample size increases. The confidence interval decreases, the width decreases, as the sample size increases. And you can get the reason for that if you take a look back at the formula right here. As you increase the size, think about this, as you increase the size, the overall fraction sigma over square root of n is going to be smaller. And so a smaller number times z, the critical value, is going to be a more narrow interval, right? The margin of error is going to be smaller because this denominator is bigger. For bigger sample sizes, the margin of error is going to become smaller than this number, right? And the second thing is that the width increases as the standard deviation increases. Again, going back, as the standard deviation increases, if I take this value, if I have bigger standard deviation for my population, that means the overall fraction is going to be bigger, and the overall fraction multiplied by the critical value is going to become a larger margin of error, right? That means it's going to be increasing the width of the confidence interval. So that's a conceptual thing to think about relative to the formula. Finding the point estimate and the margin of error from a confidence interval. What if I gave you a confidence interval? How would you find the point estimate, and how would you find the margin of error, E? Well, there are these two formulas. Take the confidence interval, take the upper limit, take the lower limit, and divide by 2. It's just the average of those two. Now, if you have the mean, the sample mean, it's really easy to find the margin of error. You would just take the upper confidence interval limit, the upper limit, and subtract the mean from it, right? And you'll get the margin of error, that difference between the two. Let's do this with an example. Suppose I gave you a confidence interval that's a confidence interval for the population mean between 26 and 40, right? And if I use my formulas, then 40 plus 26, the two endpoints, 26 and 40, being added together and divided by 2 gives me 33. That's the sample mean. And the margin of error, take the upper limit, 40, and subtract from it 33, the sample mean. And you get 7 with the margin of error. That's how we would find out the sample mean and the margin of error. Okay, we did this with the proportion as well. We wanted to figure out, well, isn't there a formula that tells me how many people I should survey? And that obviously depends on the margin of error that you choose, right? So taking this margin of error formula and solving it for n will allow us to find the number of people that we should survey for a particular margin of error. Again, we know sigma here, which is highly unrealistic, really unrealistic. But so z sub alpha over 2 is the critical z-score based on the degree of confidence. E is the margin of error. And then sigma is the population standard deviation. So let's go through an example of that. If we want to estimate the mean weight of plastic discarded by households in 1 week, how many households must be randomly selected to be 99% confident that the sample mean is within 0.25 pounds of the true population mean? Okay, so we want to be within 0.25, a quarter of a pound of the true population mean. And here in parentheses, we're told the previous study indicates the standard deviation is 1.065 pounds. We'll have to use that as a population standard deviation. And so here's our formula. N is equal to critical value times sigma divided by margin of error, all of that, each of those factors to be squared. So we have 2.575 for the critical value for 99% confidence level. 1.065 is the known sigma, and 0.25 is the margin of error. We want to be within a quarter of a pound, which means if I take that, multiply, divide, and square it, I get a value of 120.3, which if you round that is 121 people, or 121 households technically, right? So if n is not a whole number, just round up to the next higher whole number. So what does, again, 121 mean from the context? It means that if we want to be 99% confident that the sample mean is within a quarter pound of the true population mean, then we should survey 121 people, right? 121 people should be surveyed. We would need to randomly select 121 households to be 99% confident that the mean is within a quarter pound of the population mean. How large will the sample have to be if we want to decrease the margin of error from 0.25 to 0.2? Would you expect it to be larger or smaller? Pause the video and decide for yourself, larger or smaller. If we do the math, if we think about decreasing 0.25 to 0.2, what does that mean? That means actually making this margin of error smaller. When we make the margin of error or the denominator smaller, the overall value should be bigger, right? The denominator gets smaller, so the overall fraction would be bigger. And that's what happens when you divide by 0.2 instead of 0.25. You get to survey more households. You'd have to survey now 189 households because you don't want to be within a quarter pound. You want to be within a fifth of a pound, which is a smaller amount of the true population mean. We would need to randomly select a larger sample because we require a small margin of error, really small margin of error. Okay. What happens when margin of E is doubled? I just want to make sure you guys are aware of this. If the margin of error is doubled, the sample size and decrease to what? Well, it's going to decrease to 1/4 of its previous amount, right? And then larger arrows allow for blank samples, smaller or larger samples, and smaller error requires blank samples. Okay, to answer those questions, 1/4 of its original value of the margin of error when it's doubled, to keep that in mind because you're squaring, right? You're squaring, so if you double, take 1 and double it, then you're actually going to square the 2 and you've decreased the sample size that's necessary to achieve that accuracy by 1/4. And then larger errors allow for smaller samples, like if we're okay to be really far away from the population mean. And the smaller errors require large samples, right? If we want to be very accurate, then we need to make sure that we sample larger, take larger samples. Keep that in mind.